Hello, and welcome back to Howdo. You just typed a question into a chat box and hit send. A second later, a paragraph appeared. Fluid, confident, accurate. Maybe it cracked a joke. Maybe it wrote you a poem. Maybe it fixed a bug in your code that you'd been staring at for 2 hours. And somewhere in the back of your mind, a small voice asked, how on earth did it do that? Because here is the thing. There is no brain behind that screen. No human typing furiously in a back room. What you just witnessed is the result of billions of mathematical calculations firing across a digital network in the fraction of a second it took you to blink. What you are dealing with is not intelligence the way you experience it. It is something stranger, more mechanical, and honestly, more fascinating. So let us pull back the curtain. Let us go inside the machine and understand exactly what is happening when an AI writes, codes, reasons, and creates images seemingly out of thin air. It starts with data, unimaginable amounts of it. Before an AI can do anything useful, it has to learn. And the way it learns is by consuming text, books, articles, websites, code repositories, scientific papers, forum posts, instruction manuals, everything. We are talking about hundreds of billions of words, trillions of characters. The collected written output of humanity compressed into a training dataset. But the AI is not memorizing any of this. That is a common misconception. It is not storing Wikipedia in a filing cabinet somewhere. Instead, it is doing something far more interesting. It is looking for patterns. Every time it reads a sentence, it is asking a silent statistical question. Given the words that came before, which word is most likely to come next? Over billions of examples, it starts to build a map. A vast, invisible web of relationships between words, ideas, and concepts. This process is called training, and it is extraordinarily expensive. Training a large language model requires thousands of specialized computer chips, called GPUs, running for weeks or even months. The electricity cost alone can run into the millions of dollars. The model is not browsing the internet when you ask it a question. It learned everything it knows before you ever opened that chat window. So what is actually inside the model after all that training? The answer is weights, specifically billions and billions of numerical values called parameters, each one a tiny dial that has been tuned during training to capture some fragment of the pattern it learned. A modern large language model can have anywhere from 7 billion to over 1 trillion parameters. Each one is just a number, but together, they encode something that looks eerily like understanding. Now here's where the magic actually happens. When you type a question and hit send, the AI does not think, it predicts. Your text gets broken into small chunks called tokens, roughly 3 or 4 characters each on average. The sentence, "How does an engine work?" might become 6 or 7 tokens. Those tokens get converted into long chains of numbers called vectors, each one representing not just the word itself, but its meaning and context. These vectors travel through the model, through layer after layer of a structure called a transformer. And at each layer, something remarkable happens. The model runs a calculation called attention. It looks at every token in your sentence and asks, which other tokens here are most relevant to understanding this one? The word engine pays close attention to how and work. The word work notices that engine is nearby. Every token is constantly updating its understanding of itself based on its neighbors. Think of it like a room full of people, all talking to each other at once, each one updating their understanding of the conversation in real time. That is what attention does. It lets every part of the sentence influence every other part simultaneously. After dozens of these transformer layers, some models use 96 or more. The processed vectors arrive at the final output stage. Here, the model looks at everything it has computed and produces a probability distribution, a ranked list of every possible next token and how likely each one is. Maybe the next token is because, 42% probability. Maybe it is since, 18%. Maybe it is the, 9%. The model picks from the top options, outputs the token, adds it to the sequence, and runs the whole calculation again for the next token. And again, and again, 30 times per second, generating one token at a time until the response is complete. That flowing paragraph you read, it was assembled one tiny chunk at a time, each piece calculated fresh based on everything that came before it. But wait, if it is just predicting the next word, why does it not just produce gibberish? Why does the output actually make sense and answer your question? This is where training gets clever. The model was not just trained to predict random text. It was fine-tuned using a technique called reinforcement learning from human feedback, or RLHF. Human trainers rated thousands of AI responses. This one is helpful, this one is harmful, this one is more accurate, this one is vague. Those ratings were used to further tune the model's weights, steering it toward responses that are useful, safe, and coherent. So when you ask an AI to write a paragraph, you are benefiting from billions of training examples, trillions of parameters, and months of human feedback, all compressed into a subset every single time you hit send. Now, what about code? How does the same model that writes poetry also debug your Python script? The answer is that code is just another kind of text, and it has patterns just like natural language does. Def function is almost always followed by a name and parentheses. If is almost always followed by a condition. Return almost always ends a function. The model learned these patterns the same way it learned that the cat sat on the is probably followed by mat. It read millions of GitHub repositories, Stack Overflow answers, and documentation pages, and it internalized the grammar of code the same way it internalized the grammar of English. When you paste a broken function and ask the AI to fix it, it is reading the structure of your code, comparing it against the patterns it learned during training, identifying where your structure deviates from what usually works, and generating a corrected version token by token. It is not running your code mentally. It is pattern matching at a level of sophistication that happens to look like reasoning. But images, surely images are completely different. They are. Image generating AI works on entirely separate principles, though it shares the same core idea of learning patterns from massive amounts of data. The most common approach today is called a diffusion model. Here is the elegant concept behind it. During training, the model takes millions of real images and deliberately destroys them. It adds random noise, like static on a television, in tiny incremental steps, until the image is pure chaos. Then it learns, step by step, how to reverse that process. How to start with noise and gradually, patiently sculpt it back into a coherent image. After training on hundreds of millions of image-text pairs, the model learns to connect visual patterns with language descriptions. The word golden retriever becomes associated with certain shapes, fur textures, color gradients, and ear structures. Sunset over mountains connects to warm color palettes, silhouetted ridgelines, and glowing horizon gradients. When you type a prompt like a robot sitting in a coffee shop, photorealistic, the model converts your words into a numerical guide, starts with an image of pure random noise, roughly 512 by 512 pixels, and then runs its denoising process typically between 20 and 50 steps, each step nudging the pixels slightly closer to what your description calls for. By step 50, the noise has been sculpted into something that looks like it was photographed. The whole process takes between 2 and 10 seconds on modern hardware. So you have text generation, code generation, and image generation. 3 seemingly different capabilities. But underneath all of them is the same fundamental engine. A neural network trained on enormous datasets that has learned the deep statistical structure of human-created content and can generate new content by predicting one step at a time what comes next. That is why AI feels so eerily capable across so many domains. It is not because it has general intelligence in the way you do. It is because the patterns in human knowledge, and whether in language, logic, or visual art, are deep and consistent enough that a sufficiently large and well-trained model can capture them and reproduce them on demand. And the models are only getting larger. GPT-4, Claude, Gemini. These are systems with hundreds of billions of parameters, trained on datasets so large that if you tried to read them yourself at a pace of 1 page per minute, it would take you longer than the entire history of human civilization to finish. The scale is genuinely incomprehensible. But here's what should stop you in your tracks. None of it understands. The model does not know what a coffee shop is. It does not feel the warmth of sunlight. It has never tasted coffee. It has only ever seen the word coffee shop next to millions of other words and images, and it has learned with extraordinary precision what tends to follow. The appearance of understanding is a side effect of scale. The pattern is so deep and the training so vast that the output looks indistinguishable from thought. So the next time you type a question into a chat box and hit send, and a perfectly formed paragraph appears a second later, you will know what is really happening. Billions of tiny dials tuned by months of training are firing in sequence, predicting one token at a time, assembling meaning from mathematics. No brain, no consciousness. Just an extraordinarily sophisticated machine, doing exactly what you trained it to do. That's howdo. See you in the next one. Thank you.